Hey, let's check out this example together as an application of the conservation of energy within the vicinity of electric field energy. Okay, so we have an electron that is accelerated from rest in a cathode ray tube, CRT, that's for short, in a zero point 0.3 kilovolt potential difference. Okay, so there's an electron and it's accelerated towards a point within a cathode ray tube through 300 volts, because zero point 0.3 kilovolts is 300 volts. Okay, find the velocity. So we need, after it's accelerated, we need to find the velocity at some point after it goes through the 300 volt zone. Okay, given that the charge of the electron is 1.6 times 10 to minus 19 coulomb, and the mass of the electron is 9.11 times 10 to minus 31 kilograms. So that's how small the mass of the electron is. Okay, for those of you who are wondering what a cathode ray tube is actually it's just like something looks like the same thing that was inside an old TV. So basically what they do is just like they expose a piece of metal to heat. That's something like one way you can do it, to heat, and because it gets too hot, this is vacuumed from air, and electrons get spit out of the metal. Once they get spit out, they get exposed to an electric field. So because they are negative charge, so they put like what we call it a grid, like a positive, and the electrons just shoot really fast, and they travel at a very fast rate. And through some magnets, they can steer them into like a certain area. For example, your old TV has the screen, so they steer it into the screen, and that's how you see the image in your old TV. Okay. So that's what the cathode ray tube is. So how do we go about solving this problem? Okay, so it's gone from rest, and the electric potential is given. So that's a good case of applying the special case where you have the charge times the voltage is equal to 1/2 mass times the velocity square. So that's it. That's the only equation you need, because we already derived it. So Q of the charge, which is 1.6 times 10 to minus 19 coulomb, and the voltage difference. So this V, although it's not written as delta V, but it represents the voltage difference. Okay, it's equal to 300 volts, and the equal sign comes down 1/2. The mass of the electron is 9.11 times 10 to minus 31 kilograms, and what's left is the velocity square. So that's one equation with one unknown. We can solve it. Solving for v square, we get the number 1.0537 times 10 to minus 10 to plus 14, I'm sorry, 10 to plus 14 meters square per second square, because this is the velocity square. But we're not looking for the velocity square. We're looking for the velocity at which the electron is traveling after accelerating through this potential grid or electric potential. And we take the square root of this, and the velocity is equal to 1.026 times 10 to the power 7 meters per second. Now this is a huge velocity. Remember, the speed of light, known as c, is 3 times 10 to the power 8 meters per second. So this is like very, very large speed. Okay, so again, this electron can go around Earth in a very short time. Okay, and that's it for this example. Thank you very much.